Hey everybody, this is Larry. This is me doing week 3 of the Leetcode weekly premium challenge. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about this one. And yay, seems like we haven't done this one before. That is, obviously it's new, it's good. Haven't done a new problem in a while. Obviously except for the contest, but yeah. So okay, let's go. Let's do this. I'm a little bit tired, but we'll see how this goes. Today we have 656 coin path is hard. You're given an integer array coins of length n and an integer max jump. You can jump to any index I of the array coins if coin sub I is not equal to 1, and you have to pay coin sub I when you visit index I. In addition to that, if you're currently at index I, you can only jump to any index I plus k, where I plus k is less than or equal to n, and k is a value in the range 1 to max jump. You're initially at position 1. You want to find the path that reaches index n with the minimum cost. Return an integer array of the index that you will visit in order so that you can reach index n with the minimum cost. If there are multiple paths in the same cost, return the lexicographically smallest one, annoying, smallest such path. If it's not possible to reach vertex n, return an empty array. A path to this, okay, yeah, lexicographic. First, I want to look at constraint. N is 1,000, so that means n squared is good. So we'll probably just do a n squared dp. I want to say that I don't know if I knew this even 5 years ago. Maybe I don't remember when I learned it, but more recent anyway. There is an n log n solution to this, right? So that is the sum. So if you really want to upsolve it, definitely think about that. I'm not gonna go over in this video. It's probably not in scope. N is 1,000. It's fine. N squared is fine. The key point about or a key thing about this type of problem is that it is path construction. I wouldn't necessarily worry that much about path construction if you're starting out, but it's not that bad, right? But we have to kind of do the actual DP first, right? And the DP is kind of, I would say, straightforward in a way, right? So let's just say we have, I don't know, how do you get min or something? I don't know, naming things is hard. And then you have an index, right? And this is going to be a kind of a straightforward DP, right? So yeah, I'm not going to go over it in that much detail. It is a hard problem. I'm lazy. But yeah, if index is greater than equal to n, then we just return. Wait, where do we suppose to end? Index n, right? So yeah, so let's just say 0. We go greater than that. Wait, is it in? No, it's the last index, right? So okay. It's a little bit awkward. Do we have to pay? If you had I, you pay. No, when you jump to I, you pay I. Okay, so you always have to pay the last index. Okay, but let's just say if it's return infinity, right? So that we don't go out of bounds. This is basically an out of bounds thing. So then now if index is equal to n minus 1, then you're done, and then you return coins of n minus 1, right? Okay, so that's the base case. And then you just do a for loop, right? So for I in range from what happens if it's -1? Will we just ignore it? I guess so. Because for example, it's not possible. Okay. Yeah. So in a way, we're just going to do as brute force as possible, right? So we go to max jump plus 1, so that we do 1 to max jump inclusive, right? And then it's just going to get min index plus I, and then the cost of jumping to I, to index plus I. Actually, maybe I messed that up. It's going to be index plus I, right? So maybe I don't even need this. Right, and then we max a minute. I mean, for now, we won't worry the path of reconstruction. I want to write it in a way such that I show you one step at a time. So we'll just ignore path reconstruction for now and see if we make sure that we get the minimal answer, right? Though they don't really explain it, but that's fine. We'll figure it out. But yeah, so then best is equal to right? What are we doing? Minning? Yeah, okay. We've been minning, and this starts at infinity. Okay. Keep in mind that we're there, then we're already done. And then now we have to make sure that index plus I is less than equal to, or less than n, really, right? And that's it. No, I guess you could just break, but yeah. So that's basically the idea, and we didn't even memorize it yet. I know, that is kind of intentional, but yeah. But you can see that, and this should be fast enough, just because it's Leetcode, right? Oh, and I mean, maybe I shouldn't return, because that's not the answer, right? I want to get min. It's gonna be 3. Why? Because it goes, 1, 3, 5. So we start at 1. We jump to 3. We jump to 5. So that's 6. Did I miss something? Why would that be 3? Let me look at the other one. Well, the other one just well, that one being no makes sense, but it's not helpful either. Why would that be 3? Huh. Alright, I guess we could just print out index. Maybe I missed something. And you have to pay if you index. I mean, even regardless. 0 is 3. That's weird. 1, 2. Oh. I have to do also if. I said this out loud, but I forgot. Okay, that is what we expect. So the reason why it was showing 3 was because it tries to go to -1. So it goes to 2, -1, and then 2. So that's negative. It's 3. But I don't know how I forgot this because I was making fun of it just now. I'm tired, right? Okay, but now we know that this works, right? So there are 2 things we need to do. One is add the memoization, right? Usually I just slap on a cache on it, but for now we'll just actually write it out. And this is not that bad, right? So maybe we write times n, right? Or has cache maybe. And cache is equal to none times n. And then this is pretty straightforward. So if has cache of index, then we return cache of index, right? Otherwise, and then cache of index is equal to best. And this way we verified that we don't do anything inside. And I guess I don't even put anything anymore. I don't even run anything really. But yeah. So then now to analyze it, right? Index, what is it? It can go from 0 to n, n minus 1 really. And each index does O of max jump work, which is of course O of n, right? In the max case, I believe. Yeah. Actually, that's not even true. It's just up to 100. But in any case, yeah. So then now this is O of n times m, where m is the max jump, I guess, or j for jump, right? And that's gonna be fast enough because it's 1,000 times 100, so it's even faster than 1,000 square. I didn't actually read the constraints apparently, but yeah, right. And now because of the cache, this will be good. Okay, but for this problem, we have to get construction, right? The path reconstruction, and not just So let's go, right? So, yeah, maybe we do like R is going to get min of 0. If R is not equal to maybe if R is equal to infinity, then it's not possible, right? Then otherwise, then now you just want to trace through the steps, and the step is that literally here, instead of having a min function, we just keep track of where to go next, right? So then maybe you have a next array is equal to none times n, right? And then here you can say next sub index is equal to none, which I guess we already defined, but I just want to make it explicit for this. And then here, if best is less, or if best is greater than, because we're trying to min this function, then best is equal to this function, and we keep track of next of index is equal to index plus I. And that's it. That's all you have to do to set up. You just have to remember what is the best place to go. And then once you do that, then now we can reconstruct it by, well, taking the path again. You could do this recursively, you could do it iteratively, it doesn't really matter. But you start at the index 0 and then you trace the path that you took. Or yeah, maybe you want to just write something like this, right? And then while the last element of answer is not equal to n-1, then we just calculate what the next best move is, yeah? So append next index of the last element. And that's it. Well, that's it if I had enough parens. And that's it. If, oh yeah, I forgot. Okay, fine. I forgot that I forgot that is they wanted in one index and I have 0 index. So I don't know. Right, pretty straightforward. But yeah, all right, let's give it a quick submit. Hopefully no silly mistakes. And yeah, that's it. What's the complexity here, right? We already went over it. This is O of n times j. This is O of, actually just O of, technically O of n, but it's output sensitive, right? Because this could be adverse. Look at every item is on the queue. And that's it. That's all I have for this one. Let me know what you think. Thanks for watching. And yeah, and as you can see, this is, you know, that's the way that I wrote it in this way, is because you can see the path reconstruction is not that bad. It can feel intimidating, and of course there are more complicated versions of path reconstruction, and but this is pretty straightforward. I think one thing that actually I want to call out, and I did it implicitly, so I didn't really mention it, is that the lexicographically smallest part, because we're going forward, right? We're constructing the next element. This is why this works, is because, well, we're counting from from the smaller number first, right? And then as a result, it tie breaks. But it tie breaks in that, yeah, because if it's equal to, then I would have came later, so then you just skip it. But if you really want to make it explicit, or if you're given a problem where that is not easy to kind of get that kind of ordering, then you could also just add an if statement to keep track of which is the best position. And lexicographically smaller is one of those things that is quote unquote greedy or pairwise comparison, right? So the earlier you have a pair, yeah, at every position you want it to move up, so it should be fine as the smallest index. And that's it. That's all I have for this one. Let me know what you think. Thanks for watching. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.